Let's start. Welcome to class. Today I'm going to continue on the uninformed search that we started last session. And so just a quick review as usual. Um, so we talked about different search strategies, uninformed search strategies. We said we have breadth-first search. If, for example, you are going to first exploring all the neighbors at one level before going deeper to the next level. So basically, in the BFS, we just explore one vertex completely. We explore it, and then we finish everything at one level before we go deeper to the next level. And in the depth-first search is exactly the opposite. So we go as deep as possible in one branch before until we reach a dead end. That is, we reach a node without any child, and then we have to go back. And then we also discussed the uniform cost search that is similar to the breadth-first search, but the only difference is that in this case we also consider the cost of each path. So we choose a path based on the lowest cost. And then we also discussed the depth limited search today and iterative deepening search. But before that, I'm also going to so we already covered breadth first and uniform cost search. I'm going to explain, just quickly review them, and then explaining depth first search, which is required to understand also depth limited search and iterative deepening. And yeah, let's start. So we had breadth first. So when we talk about breadth first search, I would like you to think about a few things so that you always remember what is the strategy. So first of all, breadth means wide, right? So you always go wide, you always go horizontally, so your movement in the path are horizontal rather than vertically, okay? And then so you are exploring the nodes that are at one level before going to the next level. And so there the first bullet here says place the successors of the current state at the end of the frontier, which then behave as a first in first out queue. So what does that mean? So the successors of the current state are just like your frontier, and then current state is where you are right now, the node or the state that you are right now. And then the way that the queue works in the breadth first search is that when you want to choose between the nodes in your frontier, you look which one you entered first, and then that is the one you pop out first. And we'll better understand it with an example. So I'm just going quickly to the breadth first search example here. So we said that we have to start, for example, from the root node. Let's say our starting point is here at 1, and then we want to explore all the path. You may also have for example, a goal here, anywhere, but at this point I'm just explaining what is the search strategy. So you start from 1. Now at this level you have to at depth 1, and when I say about the nodes or states, they are the same. Now, at this level, you only have one node, right? There is only one. And then which path you can go? You can either go to 2, right? Or you can go to 3. So there is only 2 paths here. Now, as soon as you explore the path, you mark a node as visited. So for example, for 1, as soon as we explore 1, that is, as soon as we go expand it to 2 and 3, you have to mark 1 as visited. So if I go to the next slide now, you can see that right now frontier is 1, right? So frontier is whatever now in your queue that is you are going to visit it, okay? Now we have 1, and then next we mark it as visited because we visited it. We expanded 1 to 2 and 3 because these are the only two ways that we can go, right? So our frontier at this level that we are now, the frontier is 2 and 3, okay? Now, which one, we have 2 and 3 in the queue. Which one we can go right now? Should I go 2 or 3? Anyone want to answer? Okay, you can unmute and answer if you want. Yeah, okay, it matters. It depends. Yeah, you can talk. Yep. Hello. Anyone wants to answer? So the question is, we are at like this level where we have in our frontier, we have 2 and 3, right? So the nodes that are marked in blue are the visited nodes. The nodes that are marked in pink are the nodes that we are going to visit later. So they are in the queue, okay? Now, where can we go from 1? We said we can go to like 2 and 3, so we added 2 and 3. Now I want to see if I have to go from 2 onwards or from 3. So which one should I choose, 2 or 3? Anyone? If you want to answer, just please unmute your mic. Okay, sorry. Okay, so we can go to 2, like it depends. Okay, so it depends on where, like the order that you added 2 and 3 to your queue. Okay, so when we say first in, first out, means the node that was added to the queue earlier is going to be out earlier. Okay, so now in this case, because we added 2 to the queue first, then we are going to choose 2 to expand first. Okay, so this is going to be out first, or this is going to be pop out next. Now the next, okay, here. Okay, so I went one more, sorry. Now we were at this level, so we said that we select 2 because 2 was added to the queue earlier. So we selected 2, and then when we select a node, we want to like expand it, right? Where can we go from 2? We have 3 paths, right? We can go to 4, we can go to 5, or we can go to 6. Now that we like added 4, 5, 6 to the queue, you see that I added them to the queue. Now that we added them to the queue, we mark 2 as visited. So we only mark a node as visited node only and only if we explored it completely. That means that we already added all of his children to the queue, right? So now that I added 4, 5, 6 to the queue, it means that I explored 2 completely, and now I can pop 2 out of the queue. Now my queue contains all the nodes in my frontier, which are 3, 6, 5, and 4. And your frontier, or like the nodes in the queue, or the nodes that are going to be visited, as you can see, they are the nodes in your path where you have like open path you can move somewhere, right? So for example, you can move from 3, 6, 5, 4. So these are like the open or your frontier. Now we are at this level. So which one should I choose first? So we have 4, 5, 6, 3. Which one should I choose first? So as I mentioned, at each level, because we are breadth first search, we have to choose based on first in, first out, which means we have to choose the one that were added first. So Helena said 3. So why should we go from 3? Can you unmute and let me know? So our frontier are 3, 4, 5, 6. Yeah. Okay, so if we expand 3, right, the only way we can go is 7. And the reason that we expanded 3 was because 3 was added to the queue first, right? So if you check the queue, the first one in the queue is 3 because we were adding 3 at the previous depth, right? So it was added earlier to the queue. So if I even go back, you can better see at this stage, we had 3 in the queue, and then later 4, 5, 6 were added. Therefore, when we want to like pop out of like the queue, we always go first in, first out in breadth first search. So now we have to expand 3. So the only way we can go from 3 is 7, right? Now we reach to this point. So which are the nodes in the queue now? We have 4, 5, 6, 7, right? So the nodes in the frontier are 4, 5, 6, 7. And now, which one should I choose again? First in, first out. Which one came first? 4 came first. So we are going to mark first. And then because we cannot go anywhere from 4, right? We can mark it as visited. Okay, so 4 is visited. Now, where can I go next? So we are in the breadth first search. So we are like finishing the nodes at one level, the ones that are in the frontier. So I have 5, 6, 7 in my queue. I go with 5, right? Because 5 was added first. So it is going to be pop out first. So I'm going to 5. Now, because 5 had some children, so when you visit a node, we said that you can only visit a node, like fully visit a node, if you fully explored it. That means if it has a child, you have to put them in a queue, right? So I'm going back just to show you once more. So we came from here to 4, right? Because in the frontier, the pink ones are the frontier. We had 4, 5, 6, 7. 4, 1 was the one added earlier. So we popped 4 out of the queue and marked it as visited. Now, if I want to like also mark 5 as visited, it means that I have to expand all its children, which I did. So 8 and 9 are going to be added to the queue, right? Now, what are the nodes on the frontier right now at this step? That is, which nodes are going to be visited next? What are the nodes in the queue? Anyone? No one want to answer that? So we have like 8, 9, 6, 7. So we have like these 4 nodes in the frontier, right? So these are what we have in the queue. Now, which one are we going to visit next? Yeah, so it is breadth first search. So we're gonna visit 6 first because it was added to the queue first. So we pop 6 out of the queue, and then we have to, like, in order to fully visit it, we also have to see its children, but it doesn't have any child to be added to the queue, so we just mark it as visited here. Now, at this point, we have 8, 9, 7 in the queue. Which one am I going to visit next? Again, first in, first out, right? So I'm going to visit 7. And now finally I have 8, 9, 10. Again, I'm going to use first in, first out. So the nodes in the queue are 8, 9, 10. So I'm going to pop 8 out of the queue, right? And then 8 is going to be visited. Next, we are going to pop 9 out of the queue, and then 9 is going to be visited. And just please note that at these points, like 8, 9, 6, 4, they didn't have any more children, okay? So like these are like the dead end. Now we come to 9, visit 9, and then we finally visit 10, okay? And now the queue is queue is completely empty. Now, this was just an overview of the breadth-first search. We also talked about like its complexity in terms of time and in terms of also space complexity. So for instance, in terms of time, we said that the number of nodes that are generated at each level, for example, level 0, we only have one node, right? And then at level 2, we have, let's say, maximum number of nodes because we want to like compute the complexity, right? So we want to see the worst case scenario. So let's say the maximum number of nodes, like the successors, are B. Then at level 1, we have B nodes. Level 2, each of these B nodes are going to have, again, B children, right? And then again, any of like those B children at level 3 are going to have like another B nodes. So this is going to be multiplied until we reach to level D, where we have B raised to the power of D, right? This is the number of nodes at level D. And then we said, okay, if we reach a goal at level D, it means that when we are expanding the nodes, like the nodes that were expanded in level D plus 1, okay, then we have to deduct B because that is like the goal state. So we are not interested to expand that one node, and each node is expanding like by B, so we are just reducing B here. And then we talked about the space complexity and whether it's optimal or not. We said yes, BFS or breadth-first search can guarantee that it find the shortest path, and this is because it's going like level by level, right? So there is no way that there is like a path, like a shorter path to the goal, because we are already searching all the nodes at each level before going to the next level. So at the time that we reach to the goal, we made sure that we are in the shortest path. And is it going to be the least cost solution? Like overall, in general, no, because it doesn't consider any cost of the action. So it's not going to be like the least cost solution, and unless like all the step costs are equal. And then I'm just quickly skip this one because we have already explained, and I updated the slides here because I realized some of like these numbers were not accurate. So I updated this timing, which is about 17 minutes, and then this is about 28 hours. So it wasn't accurate before. And next we talked about the uniform cost search, right? So for the uniform cost search, I mentioned that this is similar to breadth-first search, and the only difference is that now we are considering the cost. So when we want to like move and choose between different paths, you want to like consider what is the path, which path has the lowest cost, and then you choose that path to move forward. And so let's see it with an example. So let's say that, for example, this green node here, this is our goal node, and then we are starting from A, okay? So what are my frontiers at this level? So the first one, at like this level, we only have A, right? So we just visit A and that's it. And then next, from A, where can we go? So you can unmute too if you want to answer. So we can go to 6B, B, okay. That's good. So we have 3 options or 3 open paths from A. We have B, C, and D, but we choose B. And every time, please note the blue and the pink mark, because both like in breadth first and uniform cost search, one thing that you want to like take care of is the queue, right? Because you want to like see, for example, which one you pop out first. So you need to know which nodes are in your queue, or like, for example, are going to be visited next. You also want to see which nodes that you have visited, right? So the visited nodes are in blue. The pink ones are the nodes that are in your frontier. which means that the nodes that are not explored yet, we just expanded them, but we haven't visited them yet. Now we could go to B, C, D, and we said that the cost of B is 2, which is like the lowest cost, so we go to B. And at each step, because what matters is the total cost, I'm going to show the total cost of reaching to each node from the root node using like this yellow circles, okay? So now next, if you want to expand B, like using your original tree that you had here, so you have to you have to check where you can go from your original tree, okay? So now from B, we could go to E and F, right? So these are your frontiers, like from here. That is like when you visit B, it means that you explored it completely, you expanded B, so it has like E and F. And now, as I mentioned before, you have to write the total cost, that is the cumulative cost, that is the cost from the root node to each node. Now the cost of like node E is 6, because from A to E we have 2 plus 4, and then the cost to reach to F is 3, because we have like 2 plus 1, 3, right? Now, which nodes are in the frontier? We visited B because we explored it fully, so we added it to the visited list. Now the nodes that are in the queue are E, F, C, and D, okay? So these are on the queue now. Now, which one should I select next? Which one so you select next? So F or C? Jonathan said F. Okay, so sorry, I didn't have to choose this. Okay, so we have these 4 in the frontier. Always you find the one with the lowest cost. Now sometimes, like this case, you have two nodes with the same cost, okay? So in that case, you have to check which one were added to your queue first, right? Because that is a first in, first out, because it's kind of a breadth first strategy. So uniform cost search is similar to breadth first search. The only difference is that you consider the cost. But of course, when the cost is the same, then you have to check which one were added first, okay? So because we added C first, so we are going to expand C next, okay? Now from C, we could only go to G, therefore we added this. And now that we fully explored C, which means that we like expanded all these children, now we can visit, we can mark C as visited, we add it to the visited list, and now our frontier are the ones in the pink, that is E, F, G, and D. And at each step, you also have to update all these costs, right? So what is the cost to reach to G? That is 3 plus 5, 8, right? So this is the total cost here now. Now let me check the chat. I see some messages here. Just see if anyone has a question. C because it's lowest and at a higher level. That's great, yes. If you have to backtrack to A, doesn't this make this worse than BFS? Looks like you have to visit almost all nodes and backtrack several times. So if you have to backtrack to A, not necessarily, so it depends. We are going to talk about like whether like uniform cost search is optimal or not at the end. So for now, we focus on the strategy, and then I'm going to explain this later. Now, at this point, at this point, what are the nodes in our frontier? The pink ones, right? So E, F, G, D, so these are the open path. Which one am I going to select? The one with the lowest cost, right, which is F. So we are going to select F. Now, if you check your original tree, you can see that F has no children. So F is a dead end because we cannot go anywhere from here. And we have not even reached the goal node. So this is a dead end. And then what else do we have? And so we also marked F as visited because we explored F, even though F didn't have any children that we could expand, but still we explored it, right? So we have to add it to the visited list. Now we have E, G, and D. Which one am I going to choose next? The one again with the lowest cost, which is D, right? So I select D, expand D, and then visit D, add D to the visited list, adding the total cost of going to H, which is 5 plus 1, that is 6, right? And now on the frontier, we have E, G, H. So you continue the same way. You have E and H with the same cost. They both have the same lowest cost. Which one should I choose first? First in, first out, right? First in, first out. So you're gonna like choose E because it was added to the list first. So who said F? Okay, so it was a while ago. So now from E, again, because E didn't have any children and we also didn't reach a goal node yet. So this is also a dead end. That means we cannot go anywhere from here. Now the frontier is G and H. Okay. So which one should I choose next? Again, first in, first out. So we should choose H. Now we have to expand H. From H, we reach to a node that we see it is a goal node, right? So we explored H and add it to the visited list here. So add it to the visited node, and we see that we have reached to the goal node. And back to the question that one of you actually mentioned, not necessarily, because we are considering costs. So it might be more efficient in cases because it is actually considering like the lowest cost. But like for example in the breadth-first search, even though we find the shortest path, it may not, like the shortest path may not be the most efficient in terms of like the lowest cost. So it depends on what is your like your strategy, choosing the right strategy depending on what is your goal. Now we talked about the uniform cost search completeness. So we said that USC is complete. And when I say complete, I mean that it will always find a solution if one exists. So if there is a solution, it guarantees that it find it. And this is basically because it is like the BFS, and it is going like level by level, finding, like exploring all the nodes. And we also talked about like this transition cost epsilon, which we said that there are like several conditions for this completeness. One of them is that the transition cost must be positive. So we ensure that like each step or each edge that we are going in our tree has like one positive cost. And this is because it is choosing based on the lowest cost, right? So if we have like a cost 0 or negative, then it may like stuck in like infinite cycle. And we want to like make sure that it expand node in always in increasing order of the cost, which it does. And in terms of time and space complexity, so we said unlike the breadth-first search, which is going to like expand your expand like in all layers, so it is going to in the order of the increasing path cost. So we always choose the lowest, the nodes with the lowest cost, right? And so it makes it complexity depending on what. So we say that we choose a path with the minimum cost, right? So what does it mean in terms of like its complexity? So what does its complexity depends on then? Anyone wants to answer? Can't find the chat anymore. So please unmute. I lost the chat. Yep, exactly. So because we said that we are choosing based on the minimum cost, so the your complexity depends on the cost of both like your optimal solution and also that like epsilon, which is the cost of like the minimum cost of like each edge. And so we said that there is a challenge here, that is if the cost of your optimal path is much higher, like compared to like that smallest step cost that we have. What does that mean? Like we said, epsilon is the cost of like the smallest step. So that's like could be a very small number. So if your, let's say, optimal cost search is a number that is much greater than epsilon, it means that we had to like explore a lot of nodes, right? Like a huge number of nodes to reach to the goal. So, and another problem is that it doesn't have, and like this issue happens because this is like the breadth first search. It doesn't have any like predefined depth limit. It just keeps searching as long as there is a cheaper path to explore, and so it can be sometimes very like slow. And then now I briefly explained about depth first search, but today we are going to focus more on it. Now in the depth first search, so I briefly explained that we move from the root node, and then we say, okay, we have, for example, several child in the frontier, and in like unlike the BFS that we were exploring all the nodes in one level before going to the next level, in the DFS we take one path and go like as deep as we can, okay, until we either reach a goal or we just reach a dead end, and then we need to backtrack, okay, if we didn't find a goal. And so for the BFS, I told you that I want you to think of it as, because it's a breadth, so I want you to think of it as search wide or search horizontal before you go vertical, okay? In DFS, it's the opposite way. So I want you to think searching vertical before going horizontal. So you take one node, go deep, 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 deep until you either reach your goal or reach a dead end. And if you reach like reach a node that doesn't have any child, and it's not your goal, then you have to start backtracking. Now, what we have here in terms of data structure is a stack, okay? So we have last in, first out. So if you are like in any kind of like DFS types of search, like depth first search, depth first limited search, or like the iterative deepening depth first search. So these are all variations of the DFS that we talked today. So in any of them, I would like to think of a stack with last in, first out order, okay? So now the order is reversed. Now, let's say we have again the same tree and we want to explore it with the depth first search, okay? So what did I say? I say two things you have to keep track of. First, you have like a, instead of a queue, now you have a stack. So you put like all these nodes that you have in your stack. Therefore, the nodes that added like to your stack later, right? They are going to be popped out first. And always search vertical before going horizontal. Now, again, I'm going to show like the visited nodes in blue and the ones that are going to be visited, or the nodes in our stack in the in pink. And sorry, I couldn't like show a very good stack here, so I just showed this stack with these like two vertical lines, but you can think of a stack. Now, the first node here, we are in the root node, so this is what we have in our stack. So this is the first node to be visited, and so just when I go to the next slides, I would like you to keep track of like this stack and the colors that are changing, okay? So that you see which ones we are visiting, which ones are in the stack, and what is the order. Now, we visit A, we pop we pop one from the stack and mark it as the visited, and we push its children, which are 2 and 3, to the stack. Now, you can go like choose any order. So you may say, I want to like put 2 first in the stack and then 3. In that way, 3 is on top of your stack. So 3 is added latest, so 3 is going to be popped first. Or what I did here was that I added, so I started from right. So I added 3 to the stack first, and then I added 2 to the stack. So 2 is on top of my stack. So 2 is added latest. So this is last in. So it is going to be out first. Okay. Now, the next node that I'm going to visit is 2, right? Because this is last in, first out. So if I click to go to the next slide, you would expect that I'm going to visit 2, right? Now, I'm going to visit 2, which means in order like to fully visit a node, as I mentioned earlier, you have to like explore all its children, like all its adjacent nodes. Now from 2, we could go to 4, 5, 6. So these like 3 nodes are going to be added to our stack, right? So this is the same concept as what we had with the queue. The only difference is that in the queue, it was like first in, first out, right? So when you are in a queue, so the one who comes first is going out first. But in the depth first, you're using like the stack as a structure. So the last one that entered is going to be out first. So now we added 4, 5, 6 to our stack. So 3 was the first one, right here. And then I added from right to left. As I mentioned, you may add from left to right. But here I added like 3, then 2, 6, then 5, then 4. So this is my stack. So 4 was added the latest. So we are going to pop 4 first. Now we reach to this point that we go from 2 to 4. So as you see, like unlike BFS that we were like going horizontal and like exploring the nodes in like one level before going to the next level, now we are like going as deep as we can in one branch. Now until we reach to the node that either is our goal or is like a dead end, like here we cannot go anywhere from 4, it doesn't have any child. So what should I do now? So at this point, because 4 is visited, we already popped 4 out of the stack. So if I go one slide before, you see that 4 was here in the stack, right? So I want you to keep track of the stack too and the colors as well. So now that we visited 4, it means that we popped it out of the stack, because the stack is only the place of like the node to keep the nodes that we want to like to visit later, not the ones that we already visited. Now we have 5, 6, 3. Which one is next? Yeah, we visit 5. Yeah, because we added 5 actually after 6, right? And this is last in, first out. So 5 is going to be popped out next. Now, if you notice, if you write your stack carefully, there is no way your like DFS is going wrong. Okay, so you can do any complex tree or graph. So the only thing that you have to really learn is how to add like the nodes into the queue for breadth first, and like adding them to the visited list. And in terms of like the DFS search, you just have to take care of your stack and like the order that you push them into the stack and the order that you want to like pop out of the stack. So again, I repeat here, I started like from right to left. For example, I added 3 and then 2 because I added 2 later to the stack. So I'm going to pop 2 first. Then from 2, we visited 4, 5, 6. Sorry, we explored 4, 5, 6, right? So I said again, because I added 6 first and then 5 and then 4. So 4 was on top of my stack, right? And then 4 was next was to be out of the stack. And then it was 5, and then it is going to be, but okay, before we go to the 6, because 5 has children, one important thing that you have to note is that for a node to be fully visited, so I'm repeating this multiple times because I want you to keep it in your mind. that when you want to like mark a node as blue, like as a visited node, it must be fully explored. So at this stage, it is not fully explored because we hadn't added like the children to the queue yet, right? So in order for 5 to be visited, we have to first add these children, which are 8 and 9, to the stack. And again, I'm adding them from right to left. So I add 9 first and then 8. So 8 is going to be on top of my stack. So if I go to the next slide, you'll see that I added 9 and then I added 8, right? And I also popped 5 out of stack because we already visited it, okay? So it's out of the stack. Now in the stack, we have all these pink nodes that are the nodes that are going to be visited next, which are 8, 9, 6, 3. Now, which one am I going to choose next? I appreciate if you... Yeah, so we choose 8 because it's at the top of our stack. And it's because we like added them the latest. And then we pop 9, right? Because we cannot go any deeper. So it actually backtrack here, and we already visited 5. So we can just go to 9, right? So these are like the backtracking side. So for example, from 8, we couldn't go further, so we backtrack to 5. And like the easier way is also just checking your stack. And then in your stack, if I go to the previous step, you see that we, for example, pop 5, add its children, which are 9 and 8. Because we added 8 latest, so we are going to pop 8 first. Because we couldn't go anywhere from 8 anymore, like we couldn't go deeper, we had to backtrack to 5 and then to 9, right? Because we also visited 5. So the next one is 9 in our stack. So we pop 9. Again, there is a dead end here, right? We cannot go any deeper, so we have to backtrack. So we backtrack to 5, right? And we visited 5, so again we have to backtrack. So the next place to go is 6, and it's actually the one on top of our stack, right? So we go to 6 now. And then again, we have visited 6. There is no place to go from here. We cannot go deeper. So we backtrack, and then we go to 3. Okay, so now from 3, we can go deeper to 5, right? And as soon as you add a child to the queue, you have to remove its parent because it's visited, right? So as soon as I add 7 to the queue, I pop 3, right? And then I pop 7 and add 10, right? So 7 is visited, and then finally 10 is visited. So this is the final DFS traversal path. Now, in terms of completeness, it is not complete, right? Can you explain why? Why DFS is not complete? Anyone want to explain? Can you, when I say complete, if you remember, I mean visiting all the nodes. So can you think of a scenario with DFS that we reach a goal, but it's not complete? Yeah, that's one thing. And another issue is that I'm going to explain it also the week after reading week with another example on the blackboard, which I prepared for today. That would be better clear this. Another problem in the DFS is that it may go into like infinite loops, especially like if you don't think of it as a tree. So if there is a graph, okay, so in graph we can have cycles, right? So for instance, you can imagine if, for example, here we had one path from 1 to 2, and then again, for example, 2 to 4, 5 to 2 again, right? So there was a loop here, or there could be a loop here. So whenever there is a graph with a loop, the problem, or like with cycles, the problem is that with the DFS, it may keep revisiting the same node indefinitely. So I will show you later that it will see, for example, A, B, A, B, A, B, or from 1 to 2, 2 to 1, and again it goes like infinitely. DFS is only complete if our search space is finite and also our cycles are handled properly. And by complete, sorry, I did a mistake. By complete, I mean that it find a solution if one exists. Okay, so the reason that it is not complete is because if there is a cycle in a graph, okay, or if it is a tree that like goes like onto infinity, so if we don't define our search space as a finite search space, then it can go like infinite and never find a solution. So that is why it is not complete. And in terms of optimality, DFS is even not optimal, right? Because you may actually like you may go like very like deep in a branch, right? While your goal like is somewhere else, and so it is not even optimal. But the only good thing, can someone tell me an advantage of DFS and when, for example, DFS search could be helpful? You can unmute to explain. So what is the advantage in DFS? What do you think? Like you can think of as a strategy that it goes like, for example, take one node and goes deeper and deeper, but it doesn't like search like all the nodes level by level. So what do you think its advantage? So let's see, someone. If the goal is at the very bottom, fastest way to possibly get somewhere or last node. So the good thing is it doesn't explore all the nodes. Okay, so if sometimes it can find the answer like very fast. That is the good thing about the DFS. So for example, in breadth first, if you remember, like it was very intense, especially like in both like time and space complexity, but especially about like in terms of like the space complexity. But with the DFS, the good thing is that it can find, sometimes it can find the solutions very fast. And so what else? So we also have the time complexity of the DFS. So how can we calculate the time complexity for the depth first? So if you remember in the breadth first, I said we start from the root node, right? And then I said, okay, so from the root node, I'm going to the next. So at this level, I'm starting like exploring horizontally before going vertically. So as at each node, for example, let's say if the maximum number of the nodes that you could expand from each node was B. So for example, let's say at level 1, you have like 2 nodes, and each of like, for example, these 2 nodes could be expanded to 2 other nodes, assuming that B is 2. And again, each of those 2 nodes were again like having 2 children. So as you move deeper into the levels, each of like your nodes are going to have B, which is the maximum number of the nodes that they can have. So this is going to be multiplied, right? Because you are exploring all the nodes at each level. And so it was like a huge number of nodes you're processing. And that was why the BFS has like a huge space complexity issue. But in DFS, the good thing is, if you see it like the time complexity now, what is the worst case scenario? Like in DFS, you're not like, let's say this is your tree, you're not exploring like all the branches, right? You're going like in one branch. And so in worst case, you're expanding like first one node and then B nodes, the next level, and then B to the power of 2 nodes, and so on. So this is not going to be multiplied, right? But this is going to be added as you go down. And so Just a question. Why did I use M here and not D? So M is the length of the longest path. So we said that in the worst case scenario, we have big O of B raised to the power of M nodes, where M is the length of your longest path in the state space. Yeah, so what is the difference between M and D? So that is what I wanted you to notice, is that D is just your the depth of your actual solution. Okay, so that is the depth where you reach your solution. But M is actually the depth, the depth of the longest path. Okay, so for example, you may reach your solution at D equal to 3, but M could go like up to 10, right? So that is why I used M here. So in worst case, we are expanding a big O of B raised to the power of M. So it goes really bad if M is much larger than D. For example, if we have a tree with, like, let's say 1,000 levels, okay, but let's say your solution is at level 4, okay, and then it may go deep up to, for example, a level 1000, while your goal is somewhere on other branches at level 4 or 5. Okay, so it may, like, the worst case is that it may like do really unnecessary searches, going very deep, especially if your solution is not that deep. And let me check the messages. So I have real issues with Zoom, working with online classes with Zoom. So every time I lose the chat. Okay. So what is D? We already explained. Depth of our solution. Thank you for explaining that. Yeah. So as I mentioned, D is the actual solution depth, but M is the length of your longest path. So for example, as I mentioned, you may have, let's say, the length of your longest path in your tree may go up to 1,100, whatever, but your goal may be at depth 4. So let me go back to this slide. Actually, I may be able to explain it even better, show you better. So let's say our goal was here, okay? And then we go like deep here, or even if it was deeper, right? So you may go really deep in one branch. So in this tree, it wasn't very deep. So for example, when we reached to 8 or 9, we stayed here because it was dead end. But imagine we could go like really long, right? Or even like here, if we had like, if 4 were continuing, so we could go like forever. And so our goal was like in another branch at like earlier depth. Now the backtrack points I explained. So for example, at each step, all the nodes in the frontier are backtrack point, and so the ones that are at each level, like the current level, are actually the siblings, right? Because they have the same parents. And in terms of the space complexity, it's not bad. It's like a linear space complexity, right? Because we are only exploring a single path at any time. So we are not like exploring all the nodes, right? So we just take one node and go deep. And so now with the depth limited search, is similar to the depth search. The only thing similar to the DFS, Depth-First Search. But if you remember, I said that DFS has this problem that may go like infinite or very long in a path. So you may not want to like spend that much time going deep. So you may want to like put some limit. So let's say you say, okay, I want to go until length or depth 5, or I want to go like up to depth 8. And then is it complete? Not necessarily, right? It may not find a solution if your goal is after the depth that you define, right? For example, if your goal is at depth, let's say 10, and then you define L, this is like your limit as depth 5, so your algorithm is only searching up to depth 5. So if your goal is not somewhere up to depth 5, it is not going to find it, right? Now, I'm going to explain one more method, which is iterative deepening depth-first search. Now that you, I hope that you understood the depth-first search clearly, and it was easy, right? Now, iterative deepening should be very easy for you. So now, take the idea of the depth-limited search one step further. So we start at some depth limit, like our first depth limit, which is 0. And then we iteratively increase the depth limit by 1. So I'm going to explain it better with an example so you see better what does it mean. Now, so at each iteration, so we have iterations, as the name suggests, iterative deepening. So we have several iterations. At iteration 0, we are at level 0. Then we go to iteration 1, level 1, iteration 2, level 2, and so on. Now, if we couldn't find a solution, or if our depth limited search fail without cutting off any nodes because of the depth limit, let me explain why we stop here. So I'm going to explain this with an example. So I'm going to start, so again, I'm using the same tree, using a different search strategy, which is iterative deepening depth-first search. So as you see, we have these different levels. So this is level 0, this is level 1, this is level 2, and this is level 3, okay? Now, I want you to, so this is the goal node. So the goal node is yellow until the last slide. So this is okay. I want you to keep track of the blue and the pink ones and see the iterations and the levels, okay? And see how it works. So this is similar to depth-first search, which means you have to think of a stack and not a queue. So again, it's like last in, first out. So we are using like the DFS. But the only difference, like the very important difference, is that it doesn't keep like one single list of like the visited nodes as we had, for example, in previous search strategies like DFS. But it only keep track of them like in each iteration, okay? So if you have any questions, I'm going to see, I see that there are some messages. I'm going to answer your questions after I explain this. So I just want to make sure that we have time to finish this. So it doesn't have like just one list of visited, all like the visited nodes. So the meaning of visited node at iterative deepening depth-first search is a bit different in a sense that when I say, for example, node 2 is visited, I mean at this level 1, okay? So now keeping that in mind, we're going to start this search strategy. So we start again from root level, which is node 1. And so this is our iteration 0, level 0, right? So 1 is visited, and then we're going to the next level. So next level, so we are in the next iteration, level 1. Now, at this level, similar to what we had before, where we can go from 1, we can go to 2 or 3, right? So these are going to be added to your stack. And because if you remember, I said that my strategy is that I'm adding them from right to left. So I add 3 to the stack first, and then adding 2 to the stack. So which node is on top of my stack? 2, right? So which node is going to be popped first? 2. Now, in depth-first search, if you remember, we were continuing here, right? But can I do it now? We have a depth like we have a limit at each iteration. So at iteration 1, I'm at level 1. So I can't go like any deeper, okay? Instead, I call it visited. So I want you to, like, at each level or iteration, ignore what is in other like the levels below, okay? So only consider everything that are on top of or upper than like this dashed red line. So let's say this is your tree, okay? So in this case, when you reach to 2 is like a dead end for us because we can't go like deeper. Now, what can I do? So I can go to 3 then, right? So 2 is visited, then you have to visit 3, and then we are done at this level. We visited node at this level, but we are not finished yet. So we go to the next iteration, okay? Now at the next iteration, so we are at level 2, so this is level 2, right? And at each iteration, it is start from the beginning, okay? So it again start from 1. So again, we are in like this blue visited node, right? Then next step, where do we go? We have 2 and 3, right? So these are added to the queue, to the stack. Now 3 was added to the stack first and then 2, so we are going to visit 2. Now can I go like deeper? So let me see the chat. There are a lot of people sending messages. So it's just the maximum height of the tree. So yes, to answer your question, Prantik, M was the maximum height of the tree because that's the maximum length of, if you mean by height length, yes, that's true. And so we restrict the depth level of the search to a specific level. So even if we are able to travel deeper in the search, we are restricted by the level number. If you're talking about like iterative deepening, yes. So at each iteration, so we are searching iteratively. At each level, at each iteration, we are increasing the depth level one by one. Oh, and what is B again? So B is like always, B is the maximum number of like the children that you can have as your friend set, or like the number of successors, okay? Or like what you have in your, like for example, from 1, the B now here is 2, right? But if you think of B like in the complexity that I was explaining, because when you want to like compute the big O, like the complexity, you always think about like the worst case scenario, okay? So you think about like B as the maximum number of children. So that is like the max number then. And so let's go back to our search. So we are at level 2. We start again from like the root node. So from 1 we come to 2. We have 2 and 3, right? But we chose 2 because it was added to the stack latest. So it is going to be chosen next. Now we want to like explore 2. Can we do it? Yes, because we are still like upper than our threshold level, right? So we are still at the like 4, 5, 6 could be explored. So we visit 2. And as you see, now you can better understand why it is type of a depth-first search, right? Because we are going like as deep as we can. Like in depth-first search, we go as deep as like our tree is, but here in iterative deepening, our limitation is by our iteration. So for example, if we are iteration 2, it means level 2, so it means we can only go up to level 2, down to level 2. So we can go as deep as here. Now, what is next? So you always have to check your frontier. So you have 4, 5, 6, 3 in your frontier. Which one should I choose? So again, if you remember in my stack, I were adding them from right to left, right? So if I added like 6, 5, 4 to my stack, then 4 was added the latest, right? So 4 is going to be out or visited first. Now, the next one should be 4. And now here 4 doesn't have any child, but even if it had children, we couldn't like go any deeper. So 4 is visited next. We couldn't go any deeper. So we backtrack and we visit 5, right? We backtrack again and visit 6. So I want to show it again to you. So if it was DFS, like depth first search, normal, regular DFS, where would you go here? You could have go to 8 and 9, right? But now you don't go because you have like this limit at iteration 2 that you cannot go any deeper. So you stay here, you mark 5 as visited, then visit 6, then backtrack again. Now at this level, because they were all visited, we backtrack to 3, right? So 6 you go to 2, 1, and then you actually backtrack from 6 to 3. Now you want to like visit 3, and you can explore also the next, right, the child, and we actually reached to the goal node, right? So this is how the iterative deepening search works. So let me see if you have any questions here. Again, I lost the chat. Why is it happening to me? Okay, interesting. I hope that you didn't type. If you have any question, please ask me. Please unmute and ask me, because again, I lost my chat. Anyone has any question? Okay, if you don't unmute, yeah, sure. Oh, sorry. Yeah, so that is why it's a combination of depth first and breadth first, because if you want to think of it as the one difference is that it's going like go back. So for example, if you're at iteration level 2, right, it doesn't seem like breadth first. It actually seemed like a depth first strategy. But if you look at like each level, then it looks like a breadth first. Okay, so it's a combination of like a depth first, right, and breadth first. I'm not sure if I'm clear. You mean it's not much different from the BFS? So maybe like in this example because it's a very simple example, so I'm thinking of like other examples that could better show the difference. Yeah, it is like in terms of like the completeness that it is sorry, I wanted to move around the tree. So if you see, for example, in when we were at like the earlier iterations, like iteration 1 specifically, it was very similar to BFS, right? Especially because we couldn't go any deeper. So if I go back here, so here, it was very similar to BFS. But as I said, if you go like, for example, to the next iteration, it doesn't look like BFS anymore, because here you start, and this is the difference. In the BFS, you don't start from here again. But now, at iteration 2, you start from beginning, right? So everything is reset. That is why I said that you don't have a visited list of visited nodes like you had in breadth first or depth first. Okay, so in breadth first or depth first, we have a list of visited nodes, but here every time it reset. So now that we are at iteration 2, right, now that we are at iteration 2, it goes up to level 2. So maybe this is misleading, this iteration 2/level 2. It starts from the root node again, so it reset everything. So it comes from here up to here. Yeah, no worries. Then let's go see the complexities. Oh my god, it doesn't move and then it's really fast. Okay, so first in terms of completeness, the iterative deepening search could be complete because it finds a solution if there is a solution, right? It in a sense that it's like BFS searching like everything in each level. So if a solution exists, it can guarantee that it finds it. And the reason is because when you're searching using this strategy, it just expands the nodes, right, iteratively, with like at each iteration you increase the depth limit until you reach the depth where your goal is, right? And in terms of the time complexity, it may seem very bad because at each iteration you start from the beginning, right? So for example, let's say you're at iteration 1, you consider level 0, 1. Iteration 2, you consider level 0, 1, 2. And in iteration like 10, you're again from like starting from the beginning. And so it may seem very inefficient, but in practice, the repeated work in terms of time is not that bad. So the overall complexity, we'll see the overall complexity just is kind of comparable to the breadth versus big O of B, which is your maximum number of children to the power of D, which is your depth. So here is your time complexity. So as you can see, at level 0, which is your root node, it is like D plus 1 multiplied by this, and the reason is because your root is going to be expanded at the number of the iteration times, right? So it is going to be like expanded D plus 1 times, and then level 1 node will expand D times, and then until we reach to B to the power of D, where it is expanded only once, right? And so this is just an example. For example, if, yeah. Mm-hmm. Yeah, it's because, for example, at iteration, if I go back so you see better. So for example, if I'm at iteration 0, so at the time that I created these slides, I thought that they are very efficient, but now I see that these are okay. Yeah, so I have a serious issue with these slides. They just go without me touching them. Okay, so so you see root level was visited at level 0, right? Again at level 1, again at level 2, iteration 2, again iteration 3. So it every time it is the node that is going to be revisited more than any other nodes, right? Because it was at the first iteration. Now, this is just an example. If, for example, your B is 4, B is like the maximum number of nodes or like the successors, and let's see, say here, say your D is 10, and then this number will be like your complexity will be 4 to the power of 10, right? And so it just wanted to say that this can even like be more efficient than the breadth first search, because nodes at limit are not expanded. But in breadth first search, for example, we expand all the nodes until we expand a goal node. Okay. In terms of the space complexity, so it's still linear. So we said this is because at any point we are only storing the current depth first search path, right? And it's backtracks. So the part of it that is like the DFS or depth first search is helping here in terms of the space complexity, because it doesn't store all the nodes, but it only store the nodes in the current depth level and the backtrack points. And in terms of the optimality, it finds the shortest path if all the costs are uniform. And so if it is like, for example, breadth first search, all the costs are uniform. So here the assumption is that we have like the unit cost edges or like unweighted edges, but if like we have like edges with like different costs or varying costs, there is another strategy. You can use like a cost bound version, which is not, we are not out of scope of like this session that we are discussing now. So do you have any question like about these different strategies that we discussed? Space complexity. Yeah. So what is your confusion here? So these are two different things. So about the space complexity, so the reason that you see is big OBD is because we have B, which B is your maximum number of child, right? And then D is your depth of the solution. Now at each point, it only store the current the nodes at the current depth first search, right? And your backtrack points at each point, and then it reset again. Okay, so it doesn't store the entire tree. So in the breadth first search, it stored the entire tree, and that is why the space was very like large, because when you reach at level D, right, and each of like those nodes have like B children again, so it was very like complex. At any point, right, at any point in time, it store like this current path, including like the nodes here and the backtrack points, but not the entire tree. Like it's unlike the BFS, it's not storing the entire tree. Okay. When we are like showing like the search strategy, you may see that eventually a lot of like nodes are explored or visited. But the thing is, as I mentioned, it's not like BFS or DFS that keep like one list of all visited nodes. It's going to be reset at each iteration. So in any point, it only stores the current depth first search path. Okay. Okay, any more question? Let me see the chat. Oh. Okay, so I assume that there is no more questions, and thank you everyone for joining the class. And I'm sorry if it wasn't as engaging as in-person class. I received like several emails this morning, and so I decided to make the class online because of the weather condition. I didn't want you to commute in this weather. So hopefully I could record the session, and I'm going to upload the recording of this week's session. So Again, apologies. I usually try to upload as soon as I can, but because my classes are back to back, I use the weekend time to uh, upload like the assignments, quizzes, or for example the recordings. Um, so just keep an eye on the uh, keep an eye on the e-class for my announcement, and good luck with your assignment. I also have um, another office hours today. Instead of 6 to 7, my office hours is 5 to 6. So hopefully see you there if you have any more questions. Okay, thank you so much. Thank you. Have a good day. Bye bye. Thank you. Have a good day. Bye. Bye. Sure. Mm-hmm. Mm-hmm. Yeah. Yeah. That is what we said. Um, because we didn't yeah, because the cost bound version is another strategy that we didn't cover in the class. So this bullet just mentioned that in case that the cost is there are varying costs, then we can use like iterative deepening cost bound approach, which only expand the path with cost below a threshold. So instead of like here in iterative deepening we had like a threshold in terms of like the depth, right? So we had like, for example, we said at this iteration we go up to this level, and then at this depth level, and then at the other depth level. But in the cost bound version, it expand the path with the cost below a threshold. So you have you're like increasing your thresholds in each iteration. Instead of increasing the depth level, you increase the that cost threshold, and so yeah, that's the difference. But you don't need to know the cost bound method. Yeah, yeah. It and in general, iterative deepening search like this IDDFS, it assume a unit cost edges. So uh, okay, no problem. Have a good day. Bye.